So we are testing the claim that the average water footprint in gallons per day of women in the U.S. is different from the average water footprint in gallons per day of men in the U.S. A sample of 43 women and 33 men and their average water footprint in gallons per day are recorded below. I'm going to test the claim using the 5% significance level, standard significance level. Assume the population variances are unequal and that the water footprints are normally distributed. And we don't have to worry about those two conditions because we have a large enough sample size, right? We have over 30 for each. We want to give our answers, final answers to 3 decimal places. I'd recommend avoid rounding in between. And we're going to use for the degrees of freedom, because this is a t-test and we don't know the population standard deviation, we're going to go with the smaller degrees of freedom rather than the more complicated version. Highly recommend, if you haven't done your own water footprint, check out the watercalculator.org and check out the estimated water usage of your lifestyle. Okay, so I am going to grab this data. Oh, interesting article here. Definitely check that out too. All right. And I'm going to drop this in my spreadsheet. So I started highlighting with my mouse and it was a little finicky, so now I'm using shift and down arrow. And where's the bottom? There it is. Oops, I went too far. Don't copy too much. So that's too little. That's just enough. All right, and then I have a spreadsheet set up here. This is a different example. These different data. Let's delete that. Let's clean this up a little bit. And then I want to paste my data in here. And my spreadsheet is designed to look at the 2 columns, assuming that one column is population 1 and the other column is population 2, in this case females versus males. And this one has, let's see, null hypothesis that they are the same mean, and alternative hypothesis is they're not the same mean. Good, that's what I want. Sometimes we might have a hint that one is less than the other, so it won't always be a not equal there. So we're going to do a 2-tailed test, so that's good. 43 and 33, that's good. That's what I was expecting. And here are my means. So the average water footprint of females is about 1950 gallons per day on average. And males is on average 1742-ish. And here are their standard deviations: wider spread among the females, smaller spread among the males. And my sample statistic is the difference in the 2 means. Now I'm going with the simple version of the degrees of freedom, which is 1 minus the smaller of the sample sizes. For those of you who are maybe taking a class that's using the more complicated version, which has quite the formula up here, that's the degrees of freedom that are sometimes used for a t-test on a difference in 2 means. Okay, I'm going for the simple one here. Based on the simple degrees of freedom, I'm going to get a 2-tailed p-value of about 10%. I have a standard error of 124 gallons per day, and my t-score on that is 1.68-ish. So we're about 1.7, 1.68 standard error away from the expected mean of 0. So again, what are we testing here? We're saying males and females, they don't have a difference in their average water usage. Based on this sample, there's a difference of 200 gallons per day on average based on 43 to 33 individuals. Is 200 much different than 0 given possible random variation in samples? And according to this, I get a p-value, a probability of 10%. So what does that mean? So let's look at that in terms of a normal distribution. I have one over here, stat key. Let's go to the stat key normal. And actually, no, I want to use the stat key tdist. And I'm going to use the 32 degrees of freedom. And I'm doing a two-tail test here, given that maybe the difference is higher, maybe females use more water, maybe females use less water. I'm not really sure, regardless of this sample. And I have a t-score of, let's call it 1.678. So that's positive, so it goes on this side. All right, so again, theoretically, which is what my spreadsheet's calculating too, there's about a 5% chance on the right, 5% chance on the left. If you put those together, you get about 10% probability. Probability of what? Well, given that we expect the difference to be 0, no difference between the average water usage in gallons per day of males and females, there's a 10% chance of finding a sample that has a more extreme difference than what we found, again, given that we expected a difference of 0. So that's the interpretation of this p-value here. Now, the p-value is greater than the standard 5%, because here I have a p-value of 5% plus 5%, which is around 10%. So in this case, I'd fail to reject the null hypothesis, meaning that a difference of 200 gallons per day is close enough to 0 given these sample sizes based on just random variation in samples of this many people. All right, so let's go back to the problem here and fill in some details. All right, so what are my hypotheses here? All right, so let's see. We have X1, 1 being the first population, 2 being the second, X being the gallons per day of an individual. And we are using this to compare to a population. So again, we're looking at population averages. So I'm looking for a mu here. All right, so order is important. So I'm going to put mu1 first, and I'm going to put mu2 second. And again, these are mu's because hypotheses are about populations. These are means, so we use mu's, not p's. And again, other options here is like X bars, but X bar is related to a sample, not a population. So that's not going to be in a hypothesis formal statement. What else do we have here? We have p's, we got a 0, we got an s and a sigma. Sample standard deviation squared, so that would be the variance. And this would be the population variance. Again, that's not what we're testing here. We're testing means. And null hypothesis for two different population means is that they're equal. Alternative hypothesis should start off again with mu1 because that's what the null did, and mu2 because that's what the alternative did. And if we had a hunch that females use more or less water, we would select less than or greater than. But in this case, we were just asked to test to see if they were different. We're testing the claim that the average water footprint of women is different. Okay, so that's just not equal. All right, our sample statistic is the difference in the mean of the females from the males, and that the spreadsheet did for me here. And I'm getting a difference in means of 208.777. Let's see, how many decimal places do we want here? 1. Okay, so 207.7, right? 208.8. The t statistic to 4 decimal places. And again, we could use the spreadsheet to round for us. We have 6779, 1.6779. And often, if the t-score or z-score is less than 2, that's close enough to whatever the null hypothesis says. And if it's greater than 2, that's usually, this is different. And we have a p-value of, let's see, about 10.3%. How many decimal places do we want here? 4 decimal places, so 0.1031. And again, you can always have the spreadsheet confirm your rounding by increasing or decreasing the number of decimals displayed. And that's a rather large p-value, so we're going to fail to reject the null hypothesis. And there's only 2 possible decisions. Now here I got a lot of options. You either reject the null hypothesis or you fail to reject the null hypothesis. That's the decision. It's always about the null. The conclusion is always about the alternative. So the alternative, if you reject the null, that means you have evidence to support the alternative. If you fail to reject, you don't have evidence to support the alternative. So there is not enough evidence to support. And then what comes next must be the alternative, which should be what's stated above here in that first sentence. So double check. There is not enough evidence to support the claim that the average water footprint in gallons per day of women in the U.S. is different from the average water footprint in gallons per day of men in the U.S. That looks pretty good. All right, now before I submit this, after I've put all my answers in there, I'm going to grab the stat key data and do a randomization test to confirm that I'm going to get a similar p-value. So I have the stat key data. Stat key is pretty easy to use. So I'm just going to copy that. Oops, too much. Perfect. All right, and then I'm going to go back to stat key. So that was the theoretical. I'm going to go back here. All right, so I'm doing a hypothesis test. So that means I'm in the 3rd column. And this is a test for difference in mean. So I want that option. My data is not one of the preloaded ones in stat key. So I'm going to have to edit this data out and paste my data in. And again, the stat key wants one column that is the qualitative variable, male versus female, and another column next to it, which is the quantitative value that I'm trying to compare. And I do have a header row, right? And run it. And so I should see that I get a similar difference in means, 208.78, 43 in the first population, 33 in the second. And my null hypothesis is that they're equal. So once I have the original sample and the null, I generate thousands of more resamples of this data. So now I have 6,000 new samples that are similar to this one right here with a little card shuffling. So I have some variation. And I want a 2-tailed test. And my difference in means is positive. So I'm going to go to the right side at the bottom and enter that value of 208.78. And stat key in this randomization gives me a p-value of 0.064 plus 0.064, which is what, 12.8% combined. A little higher than what the theoretical distribution said. Theoretically, it said it should be about 10%. Randomization distribution gave me about 12% for the p-value. Either way, it's greater than the standard significance level of 5%, meaning that this is close enough to 0 to not be a big deal. So it does not, this data set, even though the females have a larger mean water usage than the males, given the sample sizes, they're not different enough to say it could be other than 0. Why? Well, here I have 43 females and 33 males. There's a lot of males and females in the US. So given that samples will vary from place to place and group to group, and given randomization and probability, they're close enough. Nice. And again, it depends on the sample. So for this particular sample, we have no evidence that females use more or less water than males.